Okay, so I'm going to start with some unreadable system T code. Does anyone want to tell me what this function does? Okay, it does a sum. What is it summing over? A tree. What type of tree is it summing over? You've got the type of it, so that should help. So it's summing over a binary tree of natural numbers. But the type of the binary tree is nat to nat to nat to nat to nat. Why? Well, this is all due to type encodings from regular types down into system T. So in this talk, I'm going to mostly be talking about type encodings for system T, and then I'm going to go on and explain how you can use this to write a fueled self-reducer within system T. So giving a practical application for this. The type encodings are not new. They are work by Oleg Kiselyov and John Longley and Normann, but applying them seems to be new. So here's this unreadable system T code again. And if you have a look here, for instance, we have tree is applied to 4 arguments, and tree is applied to 4 arguments, and tree is also applied to 2 arguments. It seems to be doing 2 different things here. And if you look over here, we have heap is applied to 3 arguments, but it's also applied to 1. So it seems to be encoding 2 different types in the same structure. So what it's doing is the tree and heap are both encoding union types. So these are C-style unions. So they have injections and projections. So you can put data in and take data out. If you take out the same data you put in, things work well. If you take out different data, things work badly. Luckily, we'll get to remove these later on in our encoding process, but for now, we need them. This encoding is thanks to Oleg Kiselyov, and the exact structure of the projections, injections, and union depend on the types of what you're injecting and projecting from. This is only possible because system T only has functions and natural numbers. If it had any other type, this union type would not exist. So, using union types, the type of sum is now significantly harder to understand, but the code is somewhat easier to understand. So a tree, it takes a left out of it for the depth and the root, and it takes a right out of it for the heap. Similarly, for when we're looking into the heap, we take a left out of it to get a tag, and we take a right out of it to get a union. But here we can see that for the depth, root, and heap, we both apply different numbers to tree and then do a projection. And for tag and data, we apply different numbers to heap and project out the data in different ways. So this is encoding product types. So a product type is a function from a natural to a union, where if you give it the function 0, then you have a first, and if you give it a 1, you get a second. So this is, again, an encoding thanks to Oleg. So using product types, the code gets a lot easier to understand again. So we first deconstruct the tree here, and then we then deconstruct the heap argument later. Here we have an if statement based off of a tag. And on one case, we do something with the data. And in the other case, we do something else with the data. And this is tagging a union. So some of you might be thinking, tagged unions, that sounds familiar. And that's because a tagged union is just a sum. So you can encode tagged unions using you can encode sum types using tagged unions, a pair of a natural number and a union. It's a left if the tag is 0. It's a right if the tag is 1. And to do a case split, you first check the value of the tag and you apply the corresponding function. So using sum types, the code again gets somewhat simpler. We first deconstruct the tree, and then recursively, we match the value of the heap. And if it's a left, then we just return the data. And if it's a right, then that must be it's a branch. So we recursively find the sum of the tree. But it's a bit confusing how we do this, because we have a tree is a combination of a depth, root, and heap, whereas normally we just want to have a single data structure we fold over. So we need to have these 3 arguments because, as the name suggests, a tree is just stored as a heap. So each individual recursive argument is represented by a natural number that points somewhere else in the heap. We need to store the depth of the tree. So then we can do primitive recursion over it to compute the fold. If we didn't know the depth, we couldn't have a terminating program, and systemd has to have termination. And then we also store the root of the heap for efficiency reasons. So say you only want to do a case split on the outer structure of the tree. You don't want to actually do a full fold. If you didn't store the root, you would have to do a fold over the tree anyway, returning a sum type, and you have to rebuild the tree as you go all the way back up. So by storing the root, you don't have to recompute the tree every single time. You can just do it once, and that's good enough. So our final program for summing over a binary tree is, as you'd see, a sum over a binary tree. Very simple. So all of these encodings are computable within systemd, and you can also, so you apply them in the reverse order. You start with this nice language and end up with the unreadable systemd. So there's only some types, inductive types this works for. These are the regular types. So examples of regular types are lists, binary trees, finitely branching trees, and so on. So two non-examples. The first one here is a really badly behaved type. It's not even it's not strictly positive. It doesn't even have a fixed point in set. So for all the models that systemd supports, we have no chance of representing it. The second one is for countably infinite trees. So these are ones where each branch can have infinitely many children. The reason why we can't represent this in systemd is because you can't compute the depth of the tree. If you're given infinitely many children, you need to find out the maximum depth of those children to be able to find the depth of your new tree. You can't compute the maximum of an infinite amount of data in a finite amount of time. So we can't represent this data in systemd. So using these data structures, you can represent terms. So a systemd term is either a variable, it's zero, it's successor, it's the primitive recursor, abstraction, application. Pretty standard representation of terms. We're representing variables here using De Bruyne syntax because that's what we have in systemd. Other things would work, but I don't know how they would. You definitely can't do HOAS, though, because that isn't a regular type. So using this, you can define a parallel reduction step. So this takes all the beta redexes in your term and reduces them at once. It has to do it all at once because you do a fold over the tree. You can't just stop at the first one unless you have a more complicated data structure or a more complicated function. This is actually the simplest one. I'm slightly abusing syntax here. So in my fold, I'm doing a fold and I'm doing a pattern match at the same time. You can separate it out into two steps. That won't fit on my slides. So each step of your fold, you do the obvious thing. So if you have a primitive recursion and your target is 0, then you take the 0 branch. If your target is a successor, then you do an application. And for an abstraction, you do beta reduction. This substitution function is also definable within this nice type system. So using all of these things, you can iterate this step function to end up with a fueled self-reducer. So this takes a fuel function, n, an amount of fuel, n, and a term, and produces a term in the normal form if it's given enough fuel. This is somewhat unsatisfying. You want it to be able to compute the fuel itself. Unfortunately, that is impossible in systemd. It's proven impossible by Andre Bauer, because that way you could come up with the fixed point for successor, which doesn't exist. So here is how you can use these fancy types. I'm currently working on extending. So I said that the compilation program was definable in this type system. I'm currently working on actually implementing that translation within it. And then I've written a compiler from this fancy language into Scheme within Idris 2. This is a verified compiler. So it has a proven, or it proves that the term is well typed as it computes the types and does the compilation steps. And the goal is to end up with a efficient program that takes these these fancy terms, which I've called Primrose, and reduces them down into systemd. So in summary, you can encode the regular types within system T. You can use these to construct a fueled self-reducer, and I'm currently working on implementing this translation within this encoding itself. Thank you.
What kind of other programs can you write in System T? Because it seems to be the compiler constructors want to always write like a reducer for like a compiler in the language itself, but
so you can, as System T is a subset of this Primrose language, you could write a self-normalizer for System T via this encoding directly. I don't know of any other applications for using System T other than it's a really small language, so it's a really good place to test ideas on. So you don't actually have to use System T as your target language. You can use this nicer one and its equivalent.
All right, thanks.
In your representation of System T, the representation does not have any types, right?
So the representation of System T here doesn't have any types.
Yeah.
To be able to do the compilation step, you do need type annotations. It's not hard to add them to this syntax, but again, it'll just make the slide longer.
Yeah. Okay. I mean, I'm just curious whether the adding type constructor will help in terms of fewer, because there is. I guess we already know that the paper called the break through the normalization barrier, which uses type annotations to solve the problem of normalization barrier. So I'm just wondering whether it also helps here.
So unfortunately not. The type system of System T doesn't let you do any case splitting on what types you have. So even if you had imperfect information about your types everywhere, you'd still have to apply the same function throughout. So if you had some form of dependent types, like breaking through the normalization barrier does, then you can actually do some self-reduction without the need for fuel. But here, that's impossible.
I wanted. I think there is a work on typed self-representation thing. So whenever you want to write a self-reducer, it is rather easy to do it in untyped thing. But if you introduce types, then I think there is a lot of. I think there are a series of papers by whom I couldn't remember, but I wonder if there is any connection to the work there.
So this is a typed fueled self-reducer. So all the problems of overhead for representing typed self-reduction also apply here, with the added benefit of having to compute the amount of fuel you need to reduce as well. So it's even less efficient in some sense.
Any other? We have some more time. Okay.
It's more about motivation. So why do you choose the system app as a target for this project?
So, long story short, I was trying to do something else, and System T was a nice, convenient place to start because it has natural numbers and functions, and that's all I needed at the time. And through a long series of extra steps, I ended up writing a self-reducer for it. And when I wrote that self-reducer, I used these type encodings. So it's an accident that this happened. It wasn't an intent.
Okay. Thank you very much.